There is one feature that truly distinguishes our species from all others, and that is we have this deep yearning, this deep desire to understand the universe, right? We are not at all willing to simply look out and accept that the world is as it is. We have this passionate drive to try to find the deep underpinnings of reality, and then, with that understanding, we want to go out into the world and mold and shape and control our surroundings, right? I mean, and this urge to understand, this urge to explore, it is utterly basic to human nature. I mean, for many of us, it surfaces even before we learn language, right? I mean, little kids constantly smashing things together, pulling them apart, trying to figure out what they're made of and how they work, right? That's how we are. And this was brought to me in one of the most clearest ways not too long ago when, back in the United States, I was speaking with a group of second grade students, little kids. Now look, I work on theoretical physics, the mathematics behind unified theories, so for the most part, I address adult audiences like yourselves. But I was in front of this group of second graders, and I wanted to give them an opportunity to show me what they'd learned in math and science, right? So I asked them a pretty basic question. I said, how do you do 3 into 6? A bunch of kids raised their hands. I pick on one girl, and she charges up to the blackboard, and she draws this big 6 and puts a 3 into it. Now, this was clearly not the answer that I was looking for, right? But for me, it was a sparkling moment because it so clearly articulated how we all begin as these uninhibited, unabashed explorers into the unknown. This little girl, she wasn't concerned with being right or wrong. She wasn't concerned with trying to please me, the expert in the room. She simply was presented with a puzzle, a problem. She came up with a course of action, and she went forward into the unknown to try to figure it out. And that's who we are, right? That's how we begin. There's a wonderful other story that you've probably heard. It's not my own. I learned it from my friend, the great educator Ken Robinson, a kind of personal hero of mine. And he tells a story again of second graders who are all at their desk, they're drawing, and a teacher goes up to one of the little girls and says, "What are you drawing?" And the little girl says, "Well, I'm drawing the face of God." And the teacher says, "Wow, I mean, how are you going to do that? Nobody knows what God looks like." And the little girl fires back, "In a minute they will." That's how we begin. That's how we take on the world when we are little, when we are young. But so many of us, we lose that spirit as we get older, right? And it is the great scientists and the great engineers who never lose that childlike spirit, that childlike wonder, that pure drive to understand and grasp how the universe works. And we have seen that when ever more refined versions of that understanding of the universe, when that understanding gets into the right hands, when it gets in the hands of those members of our species that have the most creative outlook on the world, it can yield spectacular technological disruption, innovation, and those developments in turn, we all know, can dramatically drive economic growth. But here is my point. If you follow any of those chains of disruption all the way back to the source, you inevitably run into fundamental science, basic science, science that was not pursued for some kind of application or some kind of return on investment. You find science that was pursued for its intrinsic interest. So the real fuel that drives economic growth is investment in fundamental science and basic science. And the reason for this, I think, is pretty clear. Investment in basic science creates a pervasive culture of discovery, of innovation, of exploration. And it's that culture that distinguishes between those countries that will follow and those that will lead. And what I'd like to do here this morning is flesh out that point by focusing on a couple of recent breakthroughs in what's country called big science, breakthroughs that really give us a sense of that innate drive to understand, but breakthroughs that also allow us to clearly see the vital interplay between science and government. And the timing of this talk is particularly fortuitous because we're now at an anniversary of two areas of science, the two that I'm going to focus on, right? Yesterday was the one-year anniversary of the announcement of the first direct detection of gravitational waves. I mean, how many people are familiar? How many people followed that a year ago yesterday? Right, a handful of you. So these are ripples in the fabric of space. And the detection of these represented the culmination of a 40-year research project, more than $1 billion of investment involving thousands of scientists from more than 15 countries. So part of my remarks this morning are going to focus upon how big science plays out when we are examining the universe on its largest of scales. By contrast, the other piece of science that I'm going to focus upon is focusing on the smallest of scales, because we, this year, are celebrating the 90th anniversary of the experiment which established the radical new quantum laws, quantum mechanical description of the microscopic world. And those laws initially seemed like abstract, esoteric knowledge about the structure of matter, but yet, in the 9 decades since, those insights have led to, among other things, the trillion-dollar consumer electronics industry, an industry that's projected to grow to $3 trillion globally, and all came from these insights into quantum physics. So I'll also spend part of my time focusing upon big science as it plays out when we examine the universe on its smallest of scales. And at the end, if there's time permitting, I'm going to spend a little bit of time talking about education, which of course is the pivotal driver that will allow us to continue to explore and discover going forward. All right, so let's begin with the first discovery, talking about this detection of gravitational waves. And this discovery rests upon Einstein's general theory of relativity. And look, I know that we all lead busy lives. You all in particular, you know, you're running the world, and because of that, sometimes you let your understanding of the general theory of relativity get a little bit rusty. So I'm going to spend a little time giving you a little bit of a refresher of what Einstein was talking about with his theory, and that will then take us up to this breakthrough that happened a year ago yesterday. Okay, so the general theory of relativity, it is a theory of how the force of gravity works. And of course, if we really want to understand the story of gravity, we should go a little further back. We should go back to the late 1600s, when Isaac Newton was escaping the scourge of the Black Death that was waging this winning war against humanity. So he goes from Cambridge University to the relative safety of his family home in the countryside of England. And there, with the power of pure thought and calculation and observation and wonder, Newton won a very different kind of battle for all of us, because by the time it was safe to go back to Cambridge, he would throw into dazzling relief a fundamental fact about how the universe works. Because in his time away, he discovered what we now call the universal law of gravity, right? We teach it to high school kids all around the world. It simply says that every object in the universe pulls on every other with a force that depends on two things: how big the objects are, how far apart they are in space. And just to get us all on the same page, let me just show you a little visual of what that would look like. So here you have a planet, you can think of it as the Earth if you want, in orbit around a star, the sun, and the idea is that using Newton's insight, you can predict where the planets will be at any given moment, and you look up into the night sky, and the planets are just where the math says that they should be. Tremendous insight. And the beautiful thing is that the math behind this is so simple. And in talks like this, you're never supposed to show any equations, but my own philosophy is that if the equations can fit on a t-shirt, that's okay. So there it is. That's the equation that Newton found, F equals g m1 m2 over r squared. It allows us to predict all the motion of the heavenly bodies. And because of that, for a long time, everyone pretty much thought that Newton had figured out gravity. It was a done deal. And that changed in the early part of the 20th century when Albert Einstein came on the scene. Because Einstein began to think about Newton's description of gravity, and he said, look, you know, it seems to do a really good job at describing observations, but the theory doesn't actually tell us how gravity actually works. How does the sun exert a pull on the Earth? You look up, there's no rope between them, there's no tether, there's no arm that reaches out from the sun and clutches hold of the Earth. So what is the mechanism by which gravity exerts its influence? That's the question that Einstein wanted to figure out, and he spent 10 long years trying to get the answer, and the answer he finally got is utterly spectacular. It's also the one that stares you right in the face. I mean, if you have the sun here and the Earth here, the puzzle is that the only thing between them is space. How can that do anything? But Einstein's genius was to realize that space can do something. If space and time are warped and curved, they can affect the motion of objects. So sort of think of space as if it's a rubber sheet or a trampoline. And think of the sun in space. It warps the shape of that trampoline, and in that way affects the motion of the Earth, which is drawn into orbit. Let me show you a little what that would look like. So if you take a look at space here, this grid-like icon is giving us a 3D image of space, a little hard to visualize. So let me go to a two-dimensional version that captures all the ideas. So if there's nothing there, space is flat, but if you bring in the sun, the trampoline of space warps. It curves. And similarly, if you look in the vicinity of the Earth, space is also curved according to Einstein. And now focus your attention on the moon, because this is the main point. The moon is kept in orbit because it's rolling along a valley in the curved environment that the Earth creates. That, according to Einstein, is how gravity works. And if you pull back, Earth is kept in orbit for exactly the same reason, rolling along a valley in this trampoline created by the sun. Again, of course, that's just an artist's rendition. There's mathematics behind this that makes it precise. And it also fits on a t-shirt, so I'm happy to show you two. These are the Einstein field equations that Einstein came up with in 1915. By 1919, this theory had been confirmed by observations. Einstein became a famous figure worldwide. But something else happened in the interim. 1916 and 1918, Einstein writes a couple of papers. And in these papers, he begins to think about the following issue. If space actually is like a trampoline, well, what happens if you have, say, kids running, jumping on a trampoline? As kids jump on a trampoline, they send ripples going off the surface, vibrations in the fabric of the trampoline. In these papers, Einstein applied that idea not to a trampoline, of course, but to the fabric of space itself. He said that if we were to have, say, objects like stars or black holes rapidly moving through the spatial environment, they would be like kids on a trampoline and cause ripples in the fabric of space itself to travel outwards. And that would look something like this. So imagine we have two neutron stars rapidly orbiting, could be black holes. They send out this steady march of ripples in the fabric of space. These are gravitational waves. Now, how would you detect those? Well, Einstein's math shows that as these waves go by any object, like the Earth, the waves will steadily stretch and compress the body that they are rolling by. Now, I should emphasize to you that this image that we have here is exaggerated. The actual calculation shows that for a typical astrophysical event, the amount of squeezing and stretching of, say, planet Earth would be less than an atomic diameter. Less than an atomic diameter. Now, how in the world can you possibly measure that? And here is where visionary thinkers, visionary scientists step into the game. People like Ray Weiss and Kip Thorne and Ron Drever and later on Barry Barish and a whole host, ultimately more than 1,000 scientists around the world, set their sights on measuring this kind of ripple in the fabric of space. And of course, it is an enormous challenge, but they come up with a very clever idea. I'll show you an image of it in a moment, but the idea is this. Imagine you build a detector that has two tunnels, one going this way and the other perpendicular to it. And you evacuate this chamber so there's nothing inside these tunnels, and you send laser beams running down the length of each tunnel, hitting a mirror and bouncing back. Well, as the light comes back, it commingles, it interferes with itself, and the pattern of that commingling is sensitive to the exact lengths of the two tunnels. So if a gravitational wave were to roll by and squeeze one tunnel relative to another, that pattern would slightly change, indicating that a gravitational wave had rolled by. So show you a picture of what that would look like. If you have a facility, you see these two tunnels going off, 4-kilometer long tunnels. If we dive into one, imagine you've got a laser beam that's going down that tunnel. It races along until it hits a mirror at the other end, and then it bounces back. And the idea is that when these laser lights bounce back and commingle, the exact length of the trajectories affects how the interference looks, gives you a possible signal that a wave had gone by. Now, actually executing this idea is an enormous challenge. You have to make sure that your detector is not sensitive to any other environmental influence, like a truck rolling by or a tree falling down or someone revving their motorcycle. Any of those vibrations could also slightly change the lengths of the tunnels. And this is why it took 40 years to get this to work. And the amazing thing is that the National Science Foundation in the United States had the foresight and fortitude to stick with this project over all of those years, not limiting its funding to some small funding cycle and forcing them to stop work on the project when things were not going particularly well. They stayed with it. And indeed, this was a risk well worth taking. Because when these devices were built, and I can show you two of them, one in Washington State, the other in Louisiana, they, on September 14th, the announcement was February 11th of last year, but it was referring to data that was received on September 14th of 2015. And I'll show you that data in just a moment, but let me tell you the story which that data conveys to us. The data that I'm about to show you establishes that there were two black holes 1.3 billion light years away. So we're talking about events that happened 1.3 billion years ago. And the data shows that these two black holes were cycling around each other, much as in that animation, and then they crashed into one another. And when they crashed into one another, they released a tremendous amount of energy. The amount of energy released was more than 50 times the combined energy output of every single star in every galaxy in the observable universe. That's how much energy was released. And that energy took the form of a fantastic tidal wave of space that started to race outward at the speed of light. Now, some of that wave, therefore, was heading toward planet Earth. At that time, of course, there was only single-celled life forms on the planet. But this wave kept rushing toward planet Earth at the speed of light. And about 100,000 years ago, that wave just reached the edge of the Milky Way galaxy. At that point, anatomically, modern humans had only just arisen, right? And this wave continues to roll forward toward planet Earth. About 100 years ago, when this wave was at about the distance of the closest stars in the constellation Pisces, a certain individual named Albert Einstein comes on the scene on planet Earth, and he starts to think about these ideas. And he's able to do those calculations in that paper predicting that there should be these things called gravitational waves. And then this wave is rushing closer and closer to planet Earth. And when that light wave is 2 light days away, they turn on those 2 machines. They were only doing an engineering one, calibrating it. It wasn't actually meant to be taking data. But then, at about 5 o'clock in the morning Eastern Standard Time on September 14th, each of these machines twitched. And they twitched in a way that confirms that indeed everything that I just told you in that story is correct. So let me show you how they twitched. Can you hear that? That's it. That is the sound of 2 black holes that collided 1.3 billion years ago. That is the residual wave that reached us 1.3 billion years later. An amazing story of discovery. You see, when rumors started cycling around the scientific community that this had happened, and when the word got out that there'd be a press conference on February 11th, 2016, groups of students and faculty and researchers around the world in universities and research centers all got together to watch this announcement. And I was at one of those gatherings at Columbia University in New York, and I got to tell you, when the scientists from LIGO, the name of this experiment, got up and presented the results, there was a sense in the room that I had never felt before. There was a sense in the room that everyone was just so thrilled to be human, to be alive for this to happen. There was a sense in the room that, yeah, we can dream. We can dream big. We can set ourselves lofty goals, and sometimes we can actually achieve them. And that's the kind of culture of innovation, the culture of discovery, that is vital to all of the progress that all of us hold so dear. That's what happened a year ago. Where are things going as we look toward the future? Well, there are these detectors being built in a variety of places around the world. Already in Italy, Virgo, in Germany, India, Japan. This is a truly international collaboration because you need to have many of these detectors around the world in order to triangulate the signal that comes in to figure out exactly where it came from. And the big prize, I don't know if we'll ever get there, but it would be thrilling. The big prize is to one day detect rumblings not from 2 stars crashing into each other or 2 black holes crashing into each other, but the big prize is to capture rumblings of creation itself, of the Big Bang itself. That's the promise of this kind of science and precise measurement technology going forward. All right, so that was the first piece of science that I wanted to share with you, together with its implications for the way we look at the world and see how we fit in. The second piece of science is quantum mechanics. As I mentioned at the outset, we're now celebrating the 90th anniversary of an experiment called the double-slit experiment, the prototypical experiment that established the quantum laws. And what I'd like to do is take you through, in just a couple of slides, what that experiment was, what it led to, and then we can take stock of this kind of big science as applied to the microscopic world. All right, so what is the double-slit experiment? Well, as the name indicates, what it is you have a gun that's firing pellets or BBs or ultimately even tiny particles like electrons. You fire that gun at a barrier that has 2 slits in it, and you record the location of all of those pellets that make it through to the other side. So let me just show you what that looks like. There's your barrier with the 2 slits. You fire, say, these pellets at it, and as you would intuitively expect, those pellets that go through the right slit land in a band aligned with it on the right, and those pellets that go through the left opening land in a band aligned with it. So there's nothing surprising in this version of the double slit experiment when you're using everyday macroscopic size objects like little pellets or BBs. But now I want to change things in one way. I want to dial down the size of the pellets, making them smaller and smaller until they are as small as tiny subatomic particles, like electrons. Now, based on your intuition, you would think that that really shouldn't make all that much of a difference. You'd think that you still pretty much get the same data. So most of us would think that this is what we would get if we did this experiment not with pellets or BBs, but with electrons. And the thing is, when you actually do the experiment, as was done in a different form back in 1927, this is not what you find. Let me show you what you actually find. So you start firing these particles, these electrons, one by one by one, and I'll speed it up. At first, they have sort of a random spray on that detector screen, but if you have patience and you wait long enough, a pattern begins to form. And that pattern, surprisingly, is not the data that you would have expected, the 2 bands. Instead, we have many bands. You've got dark next to bright, next to dark, next to bright, next to dark, and so forth. And that collection of many bands, the fact that you have many instead of 2, that represents the most dramatic upheaval in human understanding, right there. If that was 2, totally straightforward, the world of the small would be just like the world of the big. But the fact that you don't have 2 there is a huge, dramatic change in our understanding of the world. Why is that? Well, you ask any physicist, even a physics student, what they think of when they see that kind of pattern of dark, bright, dark, bright, dark, bright. And any physicist who's taken any basic physics knows that that brings to mind a completely different subject, the subject of waves. Why is that? Well, think about it. If you have a couple of pebbles and you throw them into a pond, right? The pebbles hit the water and they generate outward going water waves. Something interesting happens when the waves overlap, when they coalesce, right? There's some regions where the peak of one wave crosses the peak of another and the wave is really high. Some places where the trough of one covers the trough of another and it's really deep. But there are other places where the peak of one goes by the trough of another and they cancel each other out. And that cancellation gives rise to this kind of pattern. Let me show you what that would look like. So if we take a look at this here with water waves going toward a barrier that has 2 openings, just like the pebbles in the pond, water that gets through each opening gives a wave that travels outward. And because of the cancellations of the peak of one against the trough of another, you do get this band-like structure. Places where the water is highly agitated next to regions where it's not agitated, next to where it's highly agitated, and so forth. So what this told us is that little particles like electrons, which we imagine as being localized little dots, somehow intrinsically have a wave-like quality. Every single particle can really be described as wave-like motion. And indeed, there's an equation behind this wave-like motion, but I've shown you enough T-shirts for the day, so I won't show you that equation. But using the equation that describes how these waves associated with particles move, we gain control over how these particles move. And with that control, we can build integrated circuits. The integrated circuit arises from our deep understanding of the microscopic realm that comes from these experiments. And of course, once you have the integrated circuit, then everything takes off, right? I mean, the fact that you have a cell phone, or a personal computer, or all manner of medical technology that may have saved your life. Anything that has an integrated circuit comes from quantum physics. You are walking around with a quantum device in your pocket. So this is a beautiful example of science that was not put forward for any kind of application. I mean, if you were to discuss with the great quantum physicists of the 20th century, people like Schrodinger or Bohr or Heisenberg, even Einstein, and ask them, what is this good for? Most of them would have said, I think, well, not really much. We're just trying to understand for the intrinsic value of figuring out how the world works. And yet, 90 years later, those insights have completely changed how we live, and will completely change how we live again and again going forward. Now, that's not where our exploration of the micro world stops, right? We press on, where we keep on going. And the deeper you want to go to probe the microscopic realm, the bigger the machine that you need. And of course, I think as many of you are familiar, the state of the art of this is right here. Large Hadron Collider in Geneva, Switzerland. This is sort of the modern day pyramids, right? This is the most complex piece of machinery that our species has ever created. It's a 27-kilometer long tunnel where particles are accelerated to near the speed of light, and then they smash into each other. And in the debris from those collisions, in the energy transformations represented by these diagrams that you see here, we try to examine the microscopic realm and figure out how things work. Now, the Large Hadron Collider, I think as some of you no doubt know, was put forward in order to try to resolve a puzzle. The puzzle was, where does the mass of everything in the world come from? And I won't take you through the details, but an insight from a physicist named Peter Higgs suggested that the reason why a particle like an electron has mass is because we are actually embedded in a kind of cosmic molasses that's right here in this room, all through the universe. And as you push on a fundamental particle like an electron, it kind of experiences a drag force against that molasses. Kind of like if you threw a pebble into a bucket of molasses, you'd see that drag force acting on it. Now, if that idea was true, we should be able to test it. And the idea put forward in 1964 is that if we had a big enough machine and we slammed particles together with enough power, then we should be able to jiggle that molasses and flick off a tiny speck, flick off what we call the Higgs particle. So we build this machine. How do we build this machine? It took more than 30 countries, right? Over $10 billion. 2,500 scientists from all over the world. And indeed, as I think many of you may know, a few years ago in 2012, it was announced that this Higgs particle had been found in these kinds of collisions. Now again, this is one of those stories, much like the detection of gravitational waves. When this was announced, again, scientists, students, faculty, researchers from around the world tuned in to watch the announcement. And again, it was one of those moments where we recognized that we do have the power, we do have the creative ability to deeply understand the universe. And again, this was not done for return on investment. This was not done in order that we'd have some new gadget in our pocket. This was done as fundamental basic science to just figure out how the world works. But it is the culture of discovery that this confirms, which ultimately is the engine driving innovation. Now, I was going to end my discussion of quantum physics there, but I'm going to give you two other quick things before I wrap up. I think I'll skip over one of them quickly, but I would like to talk a little bit, finally, about education. What I'm showing you right here is some pictures from an event that I co-founded. It's called the World Science Festival. And the reason I'm bringing this up here is because it feeds directly into this notion of shifting science from the cultural outskirts, shifting science from being viewed as a subject in the classroom. How tragic it is when kids think of science in that way. Science is the rational basis for truth. And what we need to do, and what governments can do, we need to celebrate that. And we need to celebrate it in public. We need public celebrations of science, much as we often have celebrations of literature or art or music. Because science is our guide to truth. It is our guide to the future. So what we did, we created this event, which takes place each year in New York and also in Brisbane, World Science Festival in New York, World Science Festival in Australia, where hundreds of thousands of people each year come together for 5 days of immersion in all sorts of wondrous ideas. Ideas that speak to the brain, speak to cosmology, speak to particle physics, speak to sustainability. Because what governments also need to do beyond supporting fundamental research is ensure that the general public shifts their perspective on what science is all about. So I'll leave you with one final thought as my time is up, which is this. I think many of you are familiar with what this picture is. Perhaps it even gets a little bit overused these days. But this picture is a view of planet Earth by the Cassini spacecraft from, of course, a vantage point that has Saturn in the image as well. This is Carl Sagan's pale blue dot. Now, one thing that's often not mentioned when this beautiful picture is shown is the language that Carl Sagan used in describing this, right? And it's particularly relevant in today's climate. He described how emperors and generals have spilled rivers of blood for the ability to be momentary masters of a tiny fraction of a dot. How utterly tragic that is, right? And the beauty of science is that it shifts our perspective from local parochial concerns and allows us to shift those faculties outward, where we look at the big universal questions. Where we came from, where are we going? What's the meaning of life? Where does life come from? What is consciousness? Those big questions, those are the universal questions that we all deeply care about. So the final thought I'll leave you with is this. Of course it's vital that governments support big science. Of course it's vital that governments facilitate a culture of innovation and exploration and discovery. But perhaps there's a flip side of this. Perhaps, ultimately, the kind of big international collaborations, like the one that found gravitational waves, like the one that found the Higgs boson at LIGO and at CERN, those kind of big international collaborations, they perhaps can be a model. Perhaps they can lead the way for a new kind of global conversation among governments. And that, at least to my way of thinking, is something well worth fighting for. Thank you very much.